For a while now, I've been using this PZEM004 energy meter to log my household energy consumption. It was doing a good job until one day it decided to give me the magic smoke. So I decided to open it up and look what went wrong. There were no surprises there. As always, poor component selection and bad design were the reasons that led to its smoky, obnoxious demise, if I may call it so. For an energy meter that's supposed to work 24/7, the power supply section could have been something better than a half-wave rectifier, which is expected to rectify 230 volts AC continuously for its lifetime. It's not a surprise that the electrolytic capacitor decided to go ballistic. This must have caused a short because its aluminum casing landed on a component, creating a short circuit path that led to the AC mains dumping its current into the sensitive components, thus frying them. Had the design included a simple fuse for short circuit protection and a varistor to arrest the voltage spikes, this could have been avoided to a certain extent. At this point, I realized any attempt to repair it was just futile. Upon closer inspection, I found that the whole system is based on an IC called SD3004. To know what it is, I went through its datasheet and learned that it was a dedicated energy measurement system on chip with a built-in microcontroller and ability to drive different displays and also support different communication protocols. Hey, look! Even the application circuit talks about an overcurrent protection and an overvoltage protection. Here, the sensor used to measure the current is a current transformer. As you can see, there are no clear markings or any information about the current transformation ratio of this current transformer. So I guess it's up to me to find out the current transformation ratio. This led me to the topic of today's video. What is a current transformer and how do we use it to measure AC current? Hey guys, welcome to the Knurd Lab. Unlike power transformers which are used in power distribution systems, a current transformer is used as a sensor or an instrument to safely step down and measure large currents in a non-invasive manner. To achieve this, the primary side usually consists of one turn and the secondary side a large number of turns. The secondary is also short-circuited through a burden resistor. This way, the secondary current is always proportional to the primary current, which is determined by the turns ratio. We can express it in terms of the ratio between primary and secondary currents, or the secondary and the primary voltage, or the secondary and the primary number of turns. Simply put, if you measure the voltage drop across the burden resistor and using the turns ratio, you can easily find out the primary current. Coming to the principle of operation, the alternating current flowing in the primary winding creates a flux which links through the magnetic core and induces a current in the secondary winding. This secondary current creates its own magnetic flux which again links through the magnetic core with the primary winding. The magnetic flux due to the primary and the secondary currents are always opposing each other in accordance with Lenz's law. This ensures that the secondary current is always proportional to the primary current. This enables us to determine the primary current by just measuring the voltage drop across the burden resistor. Now let's see how we can experimentally find out the turns ratio of the CT. For safety reasons, I used 9V AC to power a 10 ohm load, and by using a known burden resistance, we can easily calculate the primary and secondary currents using Ohm's law. With that being said, we are now in a position to find out the turns ratio of the current transformer. The resistors used here have 5% tolerance, so it's important to measure the actual value to reliably calculate the turns ratio. For this step, the value of the burden resistor is not critical. You can use any value between 50 and 100 ohm and make a decent measurement. A 10 ohm resistor connected across 9V AC supply forms a primary circuit. The current flowing through the primary is measured using a current transformer. A 56 ohm burden resistor is connected across the secondary of the current transformer. An oscilloscope probe is connected across the burden resistor to visualize the voltage waveform. After making sure the connections are safe, let's power up the circuit and observe the primary and secondary voltages. The tolerance of the resistors, the accuracy of the multimeter, and the delay in observing and recording the primary and secondary voltage at the exact moment which they change could all introduce a certain degree of error in the calculated value. After tabulating the observed primary and secondary voltages, now it's time to calculate the average value. This step helps to minimize the errors which may have crept into our observation owing to the factors which I previously mentioned. So, we have found that the primary voltage is approximately equal to 4.82 volts and the secondary voltage 28.7 millivolts. We have the voltage drops across the primary and the secondary resistances in our hands now. So, using Ohm's law, we can easily calculate the primary current and the secondary current. The primary current comes to about 0.49 amperes and the secondary current about 0.51 milliamperes. If we observe our results carefully, we can already see that our secondary current is about 1000 times lesser than the primary current. We can anyway substitute our primary and secondary currents in the turns ratio equation. The result shows approximately 960 turns. We can safely approximate it to 1000 turns because turns ratio is usually a whole number. So our little experiment here produced a result which is about 4% tolerance. So I would say we did a pretty decent job. Now that we have found out the turns ratio, let's see how that helps us in calculating the primary current. What the burden resistor actually does is it converts the current output of the transformer to a corresponding voltage reading. This, when combined with the turns ratio which we calculated earlier, helps us in finding out the primary current easily. Let's see. We know that the ratio of the primary and the secondary currents is a turns ratio, which we found out to be 1000. I told you that the burden resistor converts the current output of that transformer into a corresponding voltage reading. So, using Ohm's law, we can represent the secondary current as the ratio of the measured secondary voltage to the resistance of RB. And there you have it. Our primary current is 17.8 times the measured secondary voltage. With this expression applicable to this particular current transformer always, we can use it to measure any amount of primary current that's not high enough to saturate the core. All you have to do is to use the ADC of a microcontroller to measure the secondary voltage, and there you have it. However, there's a catch. If you're using the ADC to measure the secondary voltage, you must carefully select the burden resistor, which we'll see how to in a short while from now. But first, let's practically verify a calculation. Using the same setup that we used earlier to calculate the turns ratio, I just recorded the primary current using an ammeter and the secondary RMS voltage using an oscilloscope. The primary current was 0.527 amps and the secondary RMS voltage was about 30 millivolts. Now, using the expression that we just found out, I calculated the primary current to be 0.534 amperes. And we were able to calculate a current with a tolerance of just 1%, and that too manually. If we could do the same using the ADC of a microcontroller, which is not only more accurate but faster, I think we could achieve more accurate results. Now that we are going to use a microcontroller to measure the secondary voltage, the selection of the burden resistor becomes critical. We have to consider the following factors before selecting a suitable value for the burden resistor. First one is your target microcontroller. If you are going to use an Arduino, then it uses Atmega 328P microcontroller. It works on 5 volts, whereas if you decide to use the ESP8266, it works on 3.3 volts. This decides the second factor, the ADC reference voltage. For the Arduino microcontroller, it is 5 volt, whereas for the ESP8266, it is 1.1 volt. And there are certain ADC ICs and breakout boards which allow you to set the reference voltage. So this plays a major role in selecting the value of the burden resistor. The next factor is the ADC resolution. The Arduino Nano, for example, has a 10-bit ADC. The ESP8266 also has a 10-bit ADC. And the ESP32, I believe, has a 12-bit ADC. Some ADC breakout boards even lets you choose between the ADC resolution that you want for your application. This takes us to the next factor, the voltage resolution. By voltage resolution, I mean the lowest possible voltage that you can measure using your ADC. In the case of the Arduino Nano, with the ADC reference voltage of 5 volt and a 10-bit ADC, the lowest possible voltage you can reliably measure is about 4.8 millivolts. This is true because each bit has two states, 0 and a 1, and in the case of a 10-bit ADC, it amounts to 2 raised to the power of 10, which is 1024. This means that the reference voltage of 5 volts is divided into 1024 discrete levels, with each level representing 4.8 millivolts. And naturally, that becomes the lowest voltage which you can measure with that microcontroller's ADC. The same is true when it comes to the maximum voltage that your ADC can measure. Since the relationship between voltage and current through a resistor, in this case a burden resistor, is a linear one, the maximum voltage that you can measure on your ADC is directly proportional to the maximum primary current that you want to measure. So it becomes all the more important to limit this secondary peak-to-peak voltage well within your maximum ADC reference voltage. If you notice one thing, the primary current that we are trying to measure is an alternating signal. So the secondary voltage is also AC. It oscillates between a positive and a negative peak voltage, and we are trying to measure an AC signal using a microcontroller's ADC, which can only measure 0 to 5 volts. Something doesn't seem correct. Well, you're not mistaken. If you recall, I said we must keep the peak-to-peak voltage of the secondary within the maximum ADC reference voltage, which is 5 volts. So all we have to do is just shift the signal upwards by 2.5 volts by exactly half of the ADC reference voltage. That's all. Finally, we found out that we have to choose the value of burden resistor such that the peak AC voltage across it should be less than or equal to plus or minus 2.5 volts. This way, when you offset the signal by 2.5 volts, you are left to work with a time varying signal. However, it just varies between 0 and 5 volts. so that your ADC can safely work with and process it. Finally, let's arrive at an optimum value for a burden resistor. Let's say a current measurement range is between 0.1 amperes and 30 amperes RMS. Though a target range is between 0.1 and 30 ampere RMS, a current transformer always sees instantaneous values of currents through it. So it's important that we design a burden resistor such that it can handle voltages corresponding to the peak value of the current that we intend to measure. This we can calculate easily because the peak value of the current is root 2 times its RMS value. So our design must be such that our ADC can handle voltages corresponding to currents between 141.4 milliamps to 42.42 amps in the primary circuit. For these primary current ranges, we can predict what kind of currents would flow through the secondary by just using the expression for turns ratio. That predicts a secondary current of about 0.1414 milliamps to 42.42 milliamps. Our ADC can only measure voltages that are greater than or equal to 4.8 millivolts and less than or equal to 2.5 volts. This means we must select a burden resistor which is able to produce a secondary voltage which is greater than or equal to 4.8 millivolts for a secondary current of 0.1414 milliamps. Likewise, the secondary voltage produced for a secondary current of 42.42 milliamps should not exceed 2.5 volts. Keeping this in mind, we can apply Ohm's law at the burden resistor for the upper and lower limits of the secondary currents we just calculated. Just like that, we arrived at the upper and lower limits for a burden resistor. The lower limit comes to about 33.94 ohm and the upper limit 58.93 ohm, which we can safely approximate it to values between 33 ohm and 56 ohm. In conclusion, the burden resistor must be less than 56 ohm and greater than 33 ohm. There's one important thing to understand here. If you choose a burden resistor closer to a lower limit, the range of currents that you can measure with your CT increases. So does your ability to measure tiny currents. But if you choose a resistor value close to its upper limit, then your range decreases and so does your resolution. This information will be handy during your programming. For my application here, I have chosen a resistor value of 56 ohm. Again, using Ohm's law, we can predict the minimum and the maximum value of voltages expected at the ADC for a measurement range, and we can safely say that they are within the limits of a ADC. With a peak-to-peak value of 4.74 volt and a peak value of 2.37 volt on either side of the 2.5 volt bias, everything seems to be fine. Now, let's design a circuit that will enable us to safely measure the voltage across the burden resistor using the ADC pin of an Arduino Nano. IP represents the primary current that we are trying to measure, and RB forms the burden resistor, the voltage drop across which is directly proportional to the primary current that we are trying to measure, and it is this voltage which goes to the ADC port of the Arduino. The resistors R1 and R2 form the potential divider which provides a bias voltage of 2.5 volt DC to the voltage across the burden resistor. To create a bias voltage of 2.5 volt, it is necessary that R1 is equal to R2 in the resistor divider. The 10 microfarad electrolytic capacitor connected across the DC bias helps to keep a smooth DC bias and also filter any noise from the measured signal. The potential divider consisting of R1 and R2, which provides the bias voltage of 2.5 volt, is actually connected to the VCC pin of the Arduino, and it is expected to be powered continuously. If a circuit is powered by a battery, then this becomes a problem because the continuous power drop across these resistors may reduce the battery life. The bias voltage can be calculated using the standard potential divider formula. In this formula, if you substitute R1 is equal to R2, then we get a bias voltage of VCC by 2, which is exactly 2.5 volts. As far as the power dissipation issue across the potential divider is concerned, you can choose an appropriate value for the R1-R2 combination using this formula so that the bias current I bias is kept within the limits. If you look at the AC voltage waveform across the burden resistor, then there is a chance that this voltage may overshoot the 5 volt and the 0 volt limit set by us. Under normal operating conditions, the chances of this occurring are remote, but when there is a fault in the circuit or a sudden inrush of current on the primary side, then this may cause the ADC to malfunction, possibly even destroying it. So, I recommend connecting a 5.1 volt Zener diode across the ADC and the ground terminal. Now that we have designed the circuit, let's quickly put everything together and see it in action. I have used a 60 watt incandescent light bulb as the load, which is powered by 220 volts AC supply. The current transformer with a burden resistor of 56 ohm is used to measure this AC current. I have connected an oscilloscope across the output of the burden resistor and the ground. To provide the 2.5 volt bias voltage, I have used a 100K potentiometer and adjusted it such that the wiper of the potentiometer outputs 2.5 volts. This forms the basic measurement circuit, and let's test the output using an oscilloscope by switching on the load. The oscilloscope is connected between the output of the burden resistor and the ground terminal. So before switching on everything, it shows 0 volts. Now if we switch on the 5 volt power supply, we could see the 2.5 volt bias voltage appearing across the burden resistor. Please note the load is not yet switched on. Now when the main supply to the load is turned on, you could see a slight increase in the RMS voltage. This is because we are measuring the signal with DC coupling. The AC voltage across the burden resistor is too small to be displayed in this setting. Now if we change our coupling to AC and increase our resolution to about 20 millivolts per division, we can clearly see the AC signal. This is the signal we are going to read with the microcontroller's ADC. It is proportional to the primary current that we are trying to measure. If you remember, we already derived the relationship between the secondary voltage and our primary current, which happens to be 17.8 times the secondary voltage. Using that, if we convert our secondary voltage of 14.75 millivolt RMS, then the primary current can be calculated to approximately 262 milliamperes, which is exactly the current that a 60 watt load would consume at around 220 volts AC. Please note that the intention of this video was to get to know the basic concepts behind measurement of AC current using a current transformer. Of course, this setup just measures the instantaneous value of the currents. To be able to get and process any useful data out of these signals like RMS, active power, reactive power, power factor, etc., we need to perform certain mathematical operations on the signal, which is of course done on the programming side. Nevertheless, it's a start, and it's always good to start from your basics. I hope to upload the follow-up to these videos in the near future. Sorry the video was a bit lengthy, but I hope I was able to cover all the basic concepts. That brings us to the end of today's video. If you think you are able to learn something useful from my content, or if I have earned your support, then please consider subscribing to my channel. Please like the video and do share it with your friends. Until I see you next time, remember, engineer, experiment, and educate.